Advanced cable manufacturing combines cutting-edge technology and precision machinery to produce high-performance wires for marine, construction, and heavy industries. In the wire rope manufacturing process, there are many important steps such as creating the link, twisting the wire rope. To create the first link, the hydraulic press will close the link by applying high pressure to squeeze the metal ends together inside the forming die. This cold forming process ensures precise alignment, strong bonding, and seamless bonding, suitable for heavy-duty applications without significant material loss. Next are the steps when the steel wires are twisted together. Each individual wire is twisted together to form strands. Then multiple strands are placed around the central core to form the entire wire rope. This process requires precision machinery to ensure uniform tension, perfect alignment, and consistent wire orientation over the entire length of the wire. The process begins with coils of high-strength steel wire that have been previously drawn, cleaned, and coated. These wires are first arranged onto bobbins and placed in a stranding machine. The stranding machine rotates multiple wire spools simultaneously while the wires are guided through forming dies. This coordinated motion twists the wires helically to form a strand. Depending on the rope design, each strand may contain from 6 to dozens of wires, laid in either right-hand or left-hand direction. Proper control of the lay length and tension is essential to guarantee strength, flexibility, and durability. Once the strands are completed, they move to the closing machine. This is where several strands, along with the central core, are twisted together to form the final rope. The closing process mirrors the stranding stage but on a larger scale. The machine's rotating cradle holds the strands while the rope is drawn through a closing die, which compresses and shapes them into a compact, stable structure. The lay direction of the rope is often opposite to that of the strands, which enhances balance and prevents unwinding under load. In modern factories, automated stranding and closing lines combine precision engineering with continuous production. The result is a perfectly balanced, high-tensile wire rope capable of meeting the rigorous demands of cranes, elevators, mining, and marine applications. In addition to the automated machinery, some stages of wire rope manufacturing still rely on skilled manual work. In smaller workshops or for custom ropes, 2 experienced craftsmen can be seen twisting and aligning the strands by hand, using simple rotating tools and guiding frames. Their precise coordination ensures correct tension, uniform lay, and perfect rope geometry. The 26 to 40 mm PP/PE Danline monofilament rope making machine is a high-capacity system designed for producing large marine ropes with 3 or 4 strands. Using polypropylene or polyethylene monofilament yarns, the machine twists and lays the strands evenly to create durable, lightweight, and strong ropes. These ropes are widely used in marine, fishing, and industrial applications. The machine features precise tension control, automatic length measurement, and synchronized twisting and winding operations, ensuring consistent rope diameter and superior quality. Its robust structure and efficient drive system allow continuous production of heavy-duty ropes suitable for demanding offshore and marine environments. The CNC rope braiding machine is an advanced system designed for producing high-quality ropes with precise control. Using computerized technology, it automatically weaves multiple strands into uniform ropes with adjustable diameters and patterns. The machine ensures consistent tension, smooth operation, and high productivity. It is widely used in manufacturing marine, industrial, and safety ropes, offering excellent strength, durability, and efficiency compared to traditional rope-making methods. A destructive test was conducted to verify the ultimate splice tensile strength of the 188 mm 7-3/4 plasma rope. Under a gradual linear pull, the rope broke at a predictable location, with a peak load of 2,423 TE. This confirms the rope's strength, based on real test data rather than theoretical values. The brake test demonstrates the cable's maximum load capacity of 400 tons, confirming its ultimate tensile strength and structural reliability under extreme tension. The non-contacting wire rope non-destructive evaluation system is designed to inspect the internal and external condition of ropes without causing any damage. The process begins with a rope moving continuously through the evaluation machine, where wires are carefully attached to guide it along the correct path. A critical feature of this method is the air gap, or liftoff, which ensures that there is no direct contact between the rope and the sensor head. This precise spacing allows magnetic or electromagnetic sensors to detect flaws, corrosion, or broken wires inside the rope, providing accurate and reliable diagnostic results for maintenance and safety assessment. Hendrik Vader Group, with over 200 years of experience in hoisting and lifting equipment, has developed an innovative asset management program. This economic and sustainable solution takes full responsibility for managing and maintaining lifting gear. After assessing the customer's equipment, experts inspect, overhaul, and maintain assets to ensure safety and readiness for future projects. Through a 24/7 accessible online database, clients can track inventory, condition, and certification. The program also offers storage, rental, and recycling services, maximizing equipment lifespan, reducing costs, and minimizing environmental impact for a more efficient and sustainable lifting operation. The DNV inspection for the huge grommet sling in our testing lab ensures compliance with strict safety standards. The process includes pre-use checks for wear or damage, periodic inspections at fixed intervals, and removal from service if critical defects are found, such as broken wires, kinks, crushing, or corrosion. Each DNV-certified sling receives a unique ID tag and a written inspection record for full traceability and certification integrity. The installation of the giant sling system, capable of lifting more than 24,000 tons, marked a milestone in offshore construction. The process began with the placement of the horizontal top part, followed by the roll-up of the bottom section in row 1. Despite earlier delays and rising costs, the assembly phase was executed with remarkable efficiency. Within just 5 days, all 4 massive modules were installed, each representing a crucial element of the platform's overall structure. The challenge intensified as the project moved offshore, where the modules had to be transformed into a single, integrated platform. These 4 modules, once interconnected, formed a colossal structure exceeding 24,000 tons in total weight. To achieve this, vast amounts of steel, pipes, and cables were meticulously joined together, ensuring strength, stability, and functionality. The complexity of this task required precision engineering and close coordination among teams, as every connection played a vital role in the platform's performance. Ultimately, this installation stood out as one of the most significant platform assemblies undertaken within the Equinor system in many years. It highlighted not only the scale of modern offshore projects, but also the capability of advanced sling technology to handle extreme lifting operations. On August 13, 2012, a remarkable engineering task took place in the Swiss Alps, the splicing of the new hauling rope for the Stock Alp Melzi Fruit gondola ropeway. The operation involved an enormous 78-ton steel wire rope manufactured by Fatzer AG Cable Works in Romanshorn, one of the most experienced cable producers in Switzerland. The rope, with a nominal diameter of 56 millimeters, a length of 6.3 kilometers, and a construction of 6 by 36 wires, was among the heaviest ever made in the country that year. After being manufactured, the rope was transported on 2 semi-trailers, each carrying one massive reel or drum with a diameter of 3.7 meters and a width of around 3 meters. Due to its extreme weight, the rope could not be transported as a single piece. It had to be unwound from one reel and wound onto another at the Linen Viaduct between St. Niklausen and Melchtal, which was the most challenging part of the transport process. Afterward, the cable was pulled from Stockalp up to Melchtal Fruit and then brought back down to the valley, where the ends were ready for splicing. The splicing process, which took place on August 13 and 14, 2012, was the true highlight of the entire project. This task required exceptional skill, concentration, and teamwork. Under the supervision of Whaley Mertz and Hannes Kohler, both expert splicers from Fatzer AG, the ends of the rope were manually interwoven for a length of 70 meters. The process was performed entirely by hand, using only traditional tools, precision measuring devices, and the long acquired experience of the workers. A total of 15 specialists from Fatzer AG, Garaventa AG, and Melzi Fruit Sportbahnen participated in the operation. They worked in perfect coordination, strand by strand, ensuring that each wire was laid correctly and under the right tension. The manual nature of the process made it extremely demanding. Every meter of the rope weighed around 12 kilograms, meaning that even a small section required tremendous physical effort. During the splicing, the workers carefully opened the outer strands, cleaned and aligned the steel wires, and then interlaced them alternately from both rope ends. Each crossover had to be precise to maintain the rope's uniform diameter and tensile strength. As the interweaving progressed, the team continuously checked the alignment and compactness of the splice, tightening each strand to avoid internal slack or uneven stress. Despite the physical strain and the cold mountain environment, the workers maintained complete focus. Their teamwork, rhythm, and experience turned this difficult task into a demonstration of traditional rope splicing craftsmanship at its finest. When completed, the 70-meter-long splice became virtually invisible, forming a continuous and secure connection that met the highest safety standards for mountain cableways. This successful operation not only ensured the safe operation of the new gondola line, but also highlighted the dedication, precision, and expertise of the Swiss cable workers. The 1 mm carbon fiber rod trial run demonstrates the testing of extremely thin yet strong carbon rods. During the process, the rods are carefully fed through precision rollers to evaluate their straightness, flexibility, and surface quality. The machine continuously adjusts speed and pressure to maintain uniformity and prevent breakage. Technicians closely observe the rod's movement and structural response under stress to ensure consistency and high performance. This trial verifies that the 1 mm carbon fiber rods meet industrial standards for strength, smoothness, and durability, making them suitable for advanced applications such as aerospace components, precision instruments, and lightweight structural parts. SPEK TRM LLC supplies cable products from well-established manufacturers such as Transmog, NOS Cable, Fujikura, EUROCABLE1, Bell Telecom Cable, Kolchikinsky Plant, and Integra Cable Systems. All supplied cables are certified by manufacturers, ensuring high quality. The company guarantees reliable deliveries, expert support, and tailored cable solutions for every customer. The wire and cable manufacturing process at General Cable begins with raw metal extraction. In the smelting process, heat and chemical reactions are used to extract pure copper from its ore. The resulting pure copper is cast into cathodes and rods, which are then sold to traders or directly supplied to cable factories. In some General Cable plants, copper rods are further processed in rod breakdown machines to reduce their size for the next manufacturing stage. In others, copper is purchased already in the required gauge size. Aluminum, another key conductor, undergoes a similar extraction and refinement process before being drawn down from aluminum rod to the desired diameter for production. Optical fiber, made from silica or glass, is another conductor type used in communication cables. It is extremely thin, about the size of a human hair, and can transmit data efficiently with minimal electromagnetic interference. Some General Cable communication plants purchase this fiber to produce fiber-optic cables for communication and military applications. Once the conductor copper, aluminum, or fiber is drawn to the correct size, it proceeds to the insulation stage. The conductor is guided through an extruder where it is coated with an insulating compound such as polyethylene, which is one of the most common materials. Plastic compounds are fed into the extruder as pellets, where heat, shear, and compression transform them into a molten state that coats the conductor. Color coatings and banding are added for identification purposes. For rubber-insulated cables, raw materials are mixed based on specific recipes. These are blended in a large mixer, strained, and formed into strips. After cooling, the rubber strips are fed into another extruder, where heat and compression convert them into a semi-liquid form that coats the conductor. The coated wire then enters a long curing tube containing high-pressure steam, water, or nitrogen, where it undergoes continuous vulcanization, CV, to harden the insulation. The insulated wire is then cooled in a water trough to maintain its shape and thickness. During every stage, advanced monitoring systems check the physical and electrical properties of the wire. Operators can interrupt production to correct any issues immediately, ensuring high product quality. A single insulated conductor may be sold as hookup wire, but most products involve combining several insulated wires. These wires can be paired, twisted, or cabled together and may include fillers, shields, and binders. After that, they are jacketed, armored, and marked with footage and traceability information. In copper communication cables, two insulated wires of different colors are twisted into pairs to reduce signal interference or crosstalk. These pairs are grouped into units or large cores, which can contain up to 200 pairs. The cores are assembled and wrapped with polyester film for protection. Coated aluminum tape or metallic shields may be applied to block external interference, while filling compounds prevent water penetration. Some buried cables even have special armor to protect against animals like rodents. For portable cords and industrial cables, multiple colored conductors, typically black, white, green, and red, are twisted together. Fillers are added to maintain roundness, and tapes or cotton layers may be wrapped around them. Shielding, braiding, and armoring operations then follow. Specialized cables like CCW designs use aluminum tape welded and corrugated around the core for maximum strength, making them resistant to gas and moisture. Finally, the cable receives an outer jacket of rubber or plastic. A print legend is applied using inkjet or wheel printing to show key details such as type, approval, and production date. The Southwire SIMpull Solutions system simplifies and speeds up parallel cable installation. The process starts with the SIMpull reel, which allows multiple cables to be pulled simultaneously without tangling. The SIMpull flange enables easy transport and setup directly at the job site. Using the Maxxis 6K cable puller, workers can efficiently pull heavy cables through conduits with minimal effort. The QWIK rope replaces traditional pull ropes, providing greater strength and flexibility. Each cable end is equipped with a SIMpull head for quick connection, while Maxxis triggers ensure safe, controlled pulling operations. Together, these tools reduce physical strain, minimize setup time, and increase productivity in modern electrical cable installation projects. The side anchor chain making machine is a specialized industrial system designed for the efficient production of anchor chains used in marine applications. The process begins with feeding preheated steel rods into the forming unit, where they are automatically bent into precise link shapes. Each link is then interlocked with the previous one to form a continuous chain. The machine uses powerful hydraulic and servo systems to ensure uniform shaping, alignment, and high dimensional accuracy of every link. After forming, the links are welded together using an automatic flash butt welding system, providing exceptional strength and reliability. The weld seams are carefully forged and heat-treated to achieve uniform hardness and eliminate any internal stresses. The chain then passes through a calibration stage, where hydraulic presses ensure consistent link size and pitch. An integrated cooling and inspection section follows, where each link is checked for weld integrity, tensile strength, and surface finish. The entire process is controlled by an advanced PLC system with digital monitoring, allowing precise adjustment of production parameters and ensuring safety and efficiency. This machine greatly improves productivity, reduces labor costs, and guarantees consistent quality, making it an essential solution for the modern shipbuilding and offshore industries. The semi-automatic anchor chain making machine is a specialized system designed for producing heavy-duty anchor chains efficiently and with high precision. The process begins with feeding pre-cut steel rods into the forming unit, where hydraulic presses bend the rods into uniform chain links. Each link is then precisely aligned and interlocked with the previous one to ensure accurate dimensions. After linking, the joints are welded by an automatic electric welder, creating strong and seamless connections. The welded links move through a calibration and shaping stage to ensure consistent size and strength. Finally, the finished chain is heat-treated to enhance its mechanical properties and durability. This semi-automatic system combines manual handling with automated operations, reducing labor intensity while maintaining flexibility in production. It is widely used in shipbuilding, offshore industries, and heavy lifting applications. The steel production process in the plant is based on 100% scrap recycling, making it highly sustainable and resource efficient. The journey begins at the Stalworks Steel Melting Shop, where high-quality steel is produced from recycled scrap. In electric arc furnaces, the scrap is melted and refined to achieve the required chemical composition and purity. Next, the molten steel is cast into billets or blooms and sent to the Kombi-Strasse, the continuous mill, where it is rolled into long products through automated and precisely controlled rolling stands. The continuous rolling process ensures consistent dimensions and mechanical properties. After rolling, the products are transferred to the ring center or coil center, where they are coiled, straightened, and cut to size according to customer requirements. Quality control and testing ensure that all specifications are met. The production line also includes the matten fabric or mesh plant, where reinforcing meshes are manufactured for construction applications, and the Profilwalzstrasse or profile mill, where various steel profiles such as angles, channels, and beams are rolled. Through the combination of modern recycling, efficient continuous production, and precise finishing, the plant achieves high-quality steel products while maintaining full environmental responsibility.